Hello everyone. In this video, we are going to look at chapter 19, section 19.3. And in this section, we are going to focus on learning this conservation of linear and angular momentum. Previously, we learned that linear or angular momentum initial plus the linear or angular impulse equals the final linear or angular momentum. In here, we talk about under the condition that if the impulse, whether it's linear, angular, that is zero, then the momentum conserved. This slide right here gives you the equation for conservation of linear momentum under the condition that if all of the linear impulse acting on the rigid body equals zero, so then you have L1 equals L2. Similarly, angularly, if some of the all the angular impulse acting on the rigid body equal to zero, then the angular momentum is conserved. Problems like this, we're going to establish the XYZ inertial frame of reference, write the conservation of linear momentum equation, write the angular momentum equation. We're going to solve our unknowns, and if it's complicated, use the kinematic equation that relate the velocity and the mass center G and the angular velocity sometimes will be needed for us to solve our problems. Let's take a look at some examples to put together. First one, we have 10 kilogram wheel that we know the mass moment of inertia Ig is 0.156 kilogram meter square. It rolls without slipping and does not rebound. We're looking for the minimum velocity to just enough to roll over that hump A there. If no slipping and rebounding occurs, so then the pivot point at A. Force at A is much greater than the weight, so we consider since the time of impact is very small, weight can be considered non-impulsive. Reaction force at A is a problem that we don't know either its direction or magnitude, so this force can be eliminated by applying the conservation of angular momentum equation about A. Starting with our angular conservation of angular momentum. Initial angular momentum equals the final angular momentum. And the rest of them really we just plug in what we do know. We do know the a lot of the variables here, and plus we're gonna plug in the relationship between linear velocity and the angular velocity, and we get a relationship between VG2 and VG1 and keep going. Next thing, so now over here we still have two unknowns, right? And we also need conservation of energy. At that, when it's passing over that little hump there, um, you have a little, because it's being elevated, you have a little potential energy. Now over there, we're looking for the minimum velocity to pass there. Minimum velocity past that little hump at A means that when we are at the highest point there, we have a velocity of zero. That is the minimum velocity to pass. That's why when we're writing here, the T3, the kinetic energy at that location 3, at that location A is a zero. So before that, the left side of the equation, before we reach point A, the potential energy is a zero. Potential energy is a zero. So you're putting the kinetic energy, translating kinetic energy, rotating together. This will be our conservation of energy equation. So relating this one and the previous one, this one together, that will give us to solve the velocity, substituting to get the velocity, angular velocity and the linear velocity. Next example, we have a mass, the sphere right here, mass center G, 3 pound ball, a velocity VG1. Initially, we have a velocity of 6 feet per second. It strike the end of the smooth 5 pounds bar, which is a rest. So initially, this thing is a rest. We're looking for the angular velocity bar about z-axis just after impact if E equals 0.5. This E equals 0.5, 0.8. We saw this before. This is whenever we have an impact, it refers to the coefficient of restitution. Now let's put that together. We know we can based on the z-axis, we can write the mass moment of inertia, and we're relating the linear velocity and the angular velocity together. We write our conservation of energy equation. Initial angular momentum equals the final angular momentum. Putting that together. Now keep in mind that initially your angular momentum will have the ball only because the bar there is not moving at all, it's at rest. After the impact, both the ball is moving, the ball is moving, the bar is moving as well. So both the ball and the bar has angular momentum. Okay, so that's one thing to keep in mind. And then we got two unknowns there. Keep going. We're going to use that value of E, coefficient of restitution, to help us uh, writing additional equation relating the velocity of bar and the velocity of the ball. Okay, so we got two equations and two unknowns. We can solve for the value of Vg and V bar, and relating the linear velocity and the radius, that we can get the angular velocity of the rod after the impact. Okay, that's all I want to share with you in this video. Hope you find it helpful, and thank you for watching.